So before all of that, let us reprise our understanding of linear kinematics. Okay, linear kinematics was all about taking a point and translating it to another position, whether it be in the X direction or the Y direction. So we've been dealing with this idea from chapters 1 all the way up to chapter 9, basically, from taking one object and translating it, from one position to the next. Xi, Xf, the difference between that is going to be a displacement, X final minus X initial. It takes a certain amount of time to change that position. That gives us our velocity, and and if we have an outside force, it's going to take a certain amount of time to change that velocity to produce an acceleration. So we've been dealing with that in a linear dynamic so far, and thus we've had equations like this. Delta X, X final minus X initial. We have velocity, delta X over delta T, acceleration, delta V over delta T. Where delta X is X final minus X initial divided by T final and T initial, we know all that. Displacement, velocity, acceleration, they're vectors. They're the ratio between a vector and a scalar, which produces another vector. Down the road, especially now that we're starting rotational dynamics, rotational kinematics, rotational motion, we're going to see that the cross product of two vectors produces another vector. It's all linear algebra, precursor into vector calculus, where we're now going to take vectors and do certain crazy things with them and produce more vectors. We're not going to do vector calculus here. That's something for you down the road, but it's all like everything leads to something. It's all a subset. It's all a precursor. So this is the linear kinematics that we've known thus far. And we've used the fact that everything operates under a constant acceleration to produce these corresponding equations. In both X and Y direction, I'm just gonna, for sake of time, show you the delta X. And for delta Y, you just use delta Y equals that stuff, and A becomes negative G. So that's our linear dynamic that we've been working with for every chapter, really. Even as we've gone into forces, energy, and momentum, we have still been in a linear perspective. Now, rotational motion or rotational kinematics is going to take all of those equations and translate them the same way, but with their angular analogs. So we're no longer going to be talking about linear displacement, linear velocity, linear acceleration, but we're going to talk about angular displacement, angular velocity, and angular acceleration, and all of those kinematics equations are going to translate into their rotational form. Then we will see the marriage between linear and rotational dynamics. That marriage happens between a translator that we call the radius. So we take everything that's going linearly around a circle and marry it to this angular component, so the angular analogs in the center of the circle by way of the radius. So we're going to take the points and translate them or stretch them out over a larger area that we call a circle. And rotate, objects are going to move linearly and rotate at the same time. A wheel, points at the edge of the wheel rotate, and the entire wheel center of mass moves as one unit. So that's a realistic picture of that marriage between linear motion and rotational motion. Before we get into all of that, let us start off by talking about the unit circle. At least in parts. So we have this line that we give a certain length, we call a radius or the circle. Theta is here. And we have this little piece of the circle we call the arc length or arc. We call that S. And we know from trig that the arc length is the product of the radius times the angle theta. So arc length equals radius times the angle. And the angle could be in radians or it could be in degrees. For our purposes, most of the time we're going to be looking at the angle in terms of radians. It's just better to use in terms of the physics of rotation, rotational motion. We know that theta is going to be the ratio between the arc length and the radius. It's a unitless quantity. S is measured in meters, radius measured in meters. So this ratio is unitless, and we call that the radian, which is the ratio of arc length over radius. So just to write that out. And that's something you should have already seen a lot of times in your math classes. If not, that's what it is. That's what the radian is. Now we're talking about a unit circle because we're going to be rotating. We're going to be taking all the points on the circle. We're going to see that different points at different positions on that circle have different velocities, have different accelerations, etc. We're going to be dealing with the physics of all that. And then some. We not just look at the arc length, we look at the entire circle. And so the distance around that circle is the circumference. We have the radius r. So for a full circle, the angle is 360 degrees. Thus we have angle theta, ratio of arc length over radius. The arc length, the total arc length around the circle, or the circumference, 2 pi r divided by r. And that gives me 2 pi radians, so which is 360 degrees. So 360 degrees, 2 pi radians. 180 is pi radians. 90 pi over 2, 60 pi over 3, 45 pi over 4, et cetera, that you've seen in many occasions. So we're just going back to that that idea. Therefore, 1 radian is 360 degrees divided by 2 pi, which is 57.3 degrees. That is the angular equivalent of the unitless radian. 57.3 degrees, 1 radian. That's how we can say, okay, now multiply that, or take 360 divided by that, we get 2 pi. Or, sorry, 6.28 radians, which is 2 pi radians. So that's where we get that logic. So it's good to just, refresh our understanding of radian and circle, because now we're going to be moving around that circle via centripetal motion, via gravitational motion, via torque, angular momentum, the kinematics, rotational kinematics. So we have to be very wise and familiar of the dynamics of circular motion, of the circle. And that even translates into wave motion as well, when we get to that. Frequencies, wavelengths, this is a translation. Sine, cosine waves translate exactly with the unit circle, 360 degrees, because of the periodicity of both of those is 2 pi. So that periodicity waveform is the same thing as the circular rotation of 360. And you keep on repeating every period, 2 pi to 4 pi, and et cetera, et cetera. So the translation is very important. It's very important to understand the circle. Okay. So so when we convert an angle in degrees to radians, for example, we can use a conversion factor. Pi radians is 180. 2 pi 360 is double it, equals to theta. Okay, theta pi radians, which is 180 degrees, all the same. Thus, if we want to convert, say, theta equals 60 degrees into radians, well, we use the conversion factor. Okay, 60 degrees. I'm going to do this and go back to the middleman. It's going to be pi radians over 180. And that gives you the radian equivalent, which is pi over 3. Or just, and so forth, 45 pi over 4, 7 pi over 8, all that stuff. But just to go one step backwards there. This is just the full conversion equation for what I just did, which is this is basically saying this is the conversion factor that you're going to use in order to convert degrees into radians that we just did. So yeah, any questions on that bit? And conversely, degrees is just the reciprocal of this 180 over pi to get radians into degrees. And it's just all conversions that we've learned back in chapter 1, 2, where we get rid of the stuff that we don't want, which is degrees, here, and we're left with what the unit in question that we want, the unknown, which is radians. And so this is going to be pi radians over 3. All right, so that should be hopefully familiar to all of us from trigonometry. So let's go back to the unit circle. Let's say that we were traveling along the circle, and instead of using points going from one position to the next, x initial to x final, we're going to be now traveling one angle to the next angle. Let's say that we have theta here. We call it theta initial because this is going to be that angle theta at this particular moment in time. And then we travel up to, say, this angle at another moment in time. I'll deal with the thetas first and then with the times. You should hopefully start to see where this is going, maybe. Well, if not, what I'm doing is I'm traveling around a unit circle, just as if I was going to be traveling from one position to the next in a certain amount of time. Velocity, angular velocity, linear velocity, angular. Okay, so I'm doing this. And then I repeat it. Periodic, harmonic motion. It's mass on spring going up and down. Waves coming in and stuff. That's not really an example of that, but it is periodic to a point. This picture is a baseline, the baseline for pretty much physics from this point until even quantum mechanics. This picture here. The understanding of all of it. So we start from the basics and we go upward. So again, counterclockwise, those are positive angles. We know that from back in the day. So if I'm now going to not go from one position to the next, I'm going from one angle to the next angle, theta initial to theta final. Well, then I don't talk about linear displacement. I'm talking about angular displacement. Therefore, angular displacement is delta theta, theta final minus theta initial, which is the angular analog of x final minus x initial. That's it. That's all it is. And this length is the radius of the circle. And if we want to do the conversion in radians and stuff like that, we won't have to do that in many problems. I mean, at some point we'll have to, try, but we don't have to do this like 50 problems of converting angles into radians like you do in math. I mean, that's for good practice, so that when you see this again, as you are now, you have a full understanding. Well, as with anything, rates of change. It takes time to change the position. Okay. Therefore, when we have velocity is delta x over delta t, we're going to now use a new variable for a new physical quantity called angular velocity, which is the translation of angular displacement over delta t. So therefore, we go from the linear idea to, well, we introduce a new variable we call omega, which is the angular velocity, which is delta theta over delta t. This is angular velocity, which is the ratio of angular displacement over time interval. Obviously, time is time for whatever coordinate system you have. So obviously, and without saying, there is no angular time. It's just time. It's not linear or angular or anything. It is. We have linear displacement above. Linear acceleration, which is delta V over delta T. And we introduce a new variable for angular acceleration, which is alpha, make it look a little similar to that, and which is going to be delta omega over delta T. So now, where do the angular quantities exist? We know that velocity is a ratio of delta x over delta t, linear, and it exists along the path of motion. But all of the angular quantities are going to be physically with respect to the center of the circle. So all of the angular quantities are going to exist here. So all of the angular velocity, angular acceleration, torque, angular momentum are all going to be produced at the center of the circle. That is the physical placement of those vectors, because we're talking about angular quantities. Here is angular acceleration. Questions, comments? So all of the angular quantities are going to be at the center of the circle. So torque, we're going to see next semester, represented by tau, lowercase. L for angular momentum. All of the angular stuff right at the center. We are going to, at least with the torque and angular momentum, we're going to see mathematically, that is vectorially, why those and the other vectors are pointing out of the center of the circle. Soon we're going to see something called the right-hand rule, which gives us an even better appreciation why those angular quantities are coming out of the center of the circle. But for right now, just labeling. We'll take it for now, but we will see the vectorial representation of that as we come to it, one step at a time. So angular displacement, angular velocity, angular acceleration. Now let's translate the linear kinematics to the rotational kinematics equations. And let's see if we have enough time to do the marriage between angular and linear quantities. So once again, so we take everything up above where it was linear displacement. I'm now traveling around a circle, no longer in a line. Although there is the linear, along the arc length, that would be the linear stuff. But with respect to the center of the circle, it's the angular stuff. So things spin or things rotate and move linearly simultaneously. Orbits, there is a linear velocity of the Earth around the sun as it rotates, moves in a circle, right? So. Oops. All right, so angular velocity, delta theta over delta t, angular acceleration, delta omega over delta t. So you can probably see, when I go up to the top, this delta x becomes delta theta, and v's become omegas, and a's become alphas. Okay, same logic. Delta theta equals 1/2 omega initial is it. And obviously, it's a conglomerate of x and y, so there are no components because you're spinning, which uses the entire plane, needless to say. Questions on that? So there's a little blurb at the end of section 1. Talks about the right-hand rule. Usually I have a wheel, have this wheel in class where I pick it up and I grab the center of the wheel, and naturally my thumb points out. That's going to be the direction of the angular quantities, your alphas, your omegas, if it spins counterclockwise. So in this picture, by the right-hand rule, if a wheel or an object in question is spinning counterclockwise as depicted here, the direction of your angular velocity, the direction of your angular acceleration, your torque, your angular momentum will be out of the page. It will be pointing towards you, out. So for counterclockwise rotations, your angular quantities will be like the tip of an arrow. And that's represented, sometimes they represent that in your book with a circle and a dot to depict the arrow coming at you, because the tip of the arrow is, all you see is the head. And the arrow on the back has got little flares like an X. So for the counterclockwise rotations, the angular quantities are out of the page. For clockwise rotations, they are into the page. So if it spins the opposite direction, it's going to go inward, represented by an X to depict as an arrow. You know, the flare on the back of the arrow is what you see. And this convention is what we call the right-hand rule, where we use our right hand to depict our fingers representing points on a circle, and our thumb representing the new angular vector, which is your angular velocity, your angular acceleration, your torque, or your angular momentum. And then if it's clockwise, your thumb is going to point inward naturally. And that's why we have that. Rotational kinematics. Okay. So that was the rotational kinematics for section 2. Again, we're going to come back to it with examples later on tomorrow. .3, I got my angular and translational quantities. Okay, so turn to that. Okay, so just briefly. Yes, no problem. Is that what you wanted?
Yeah, I got it. Thank you.
Yeah. Okay, so again, we're back at the circle. And we have radius r, angle theta, and s. This arc length is, to a certain limit, is like linear distance. It's like you're like a displacement, x. So if we were going to now, let's say, talk about linear velocity or the speed around this circle, we could say, instead of delta x, we could say delta s over delta t. Because to a certain limiting case, s is like x, displacement or position, where you are from a linear context. From an angular context, it would be in terms of the angle, angle theta. We know that s is equal to r theta. Therefore, delta s would be r delta theta over delta t. We already know that delta theta over delta t is omega, so therefore linear velocity is equal to radius times angular velocity. That's the marriage between linear quantities and angular quantities. The angular quantities are in the center of the circle. The linear quantities are at the edge of the circle. This object is changing its arc length or its length in a certain amount of time. Therefore, it has a linear velocity around the circle, angular velocity within the circle, coming from the center of the circle. So way out here, we have a particle that's under linear velocity, even as it spins around with angular velocity. So that's the marriage. It's married by the radius. That's the translator, or the transformer in linear algebra speak. It transforms linear to angular quantities by way of the radius. And the same thing goes for the angular quantity, angular acceleration. So if we take a look at acceleration, which is delta v over delta t, we know that v is r omega now. This is going to be r delta omega over delta t, because r, right? And so we just put that here. And this we've already established up top to be the angular acceleration. So the marriage between linear acceleration and angular acceleration is that equation. Questions on that? Let's see how that works. So pretty much the same thing. We just now have, we're now taking our point particle and stretching it out over a radius, which creates our circle. Spin it, rotate it, and it moves as one unit from this center of mass. Center of mass moves linearly, which is a depiction of the linear motion, and it rotates. It will not be on the final. Okay. Let's not worry about that. Okay. But it will not be on the final. So when we get the second semester, when we get into moments of inertia, center of mass, torque, we're going to take linear kinetic energy and make it rotational. That's section 10.4. If you want to take a look at that ahead of time, but everything now is going from just a point mass to a series of point masses. What I mean is, in terms of this equation, is that there are now not just this one point that we were dealing with for all of time. Now we're stretching it. We're making a series of these points, stretching it out over a radius. So now that there are successive points along the radius, that being said, every one of these points has a different linear velocity. Every one of those points has a different linear velocity. Why is that? Because they have different radii, different distances from the center of the circle where the angular velocity exists. The angular velocity, the angular acceleration, and all angular things will be the same for all points because they're all going to uniformly turn as one object, uniformly rotate. But their linear quantities are different because linearly, or they have a different linear distance from the center, a different radius. So in terms of linear velocity, this particle here will be moving slower than this one out here, linearly. Angular wise, they're all the same. And if we had an outside force, like an outside torque, which we'll be getting to, say for instance, we set this guy spinning and it's spinning around, and then we, spin it even faster by applying, putting our hand on the wheel, then now we've changed its angular velocity and its linear velocity as well. And now we have this relationship here. We now have a linear acceleration and an angular acceleration because we introduced an outside torque, which is similar to an outside force in Newton's laws, chapter 5. So that's where I want to leave it for now. Any last questions? So this bit here, hopefully you've seen that.